Well, we can compare the speed of each athlete. So Bolt, he obviously had a top speed of 11.57 meters per second, as we can see just before the deceleration phase. Now, Anning had around 1.5 seconds less at 10.18 meters per second. Obviously, I was a lot lower because I could not build up that momentum to put the speed at my highest. Now, this means that it was in fact in potentially what could be a deceleration phase of 7.28 meters per second, which was my top speed. Now, as we can see, it was within the biomechanics of speed efficiency that affected how much Bolt could go further than Anning and all the other athletes that he was competing. He would have had much stronger muscles, particularly in the glutes, hamstrings, and quadriceps, as we said. Now, this allowed him to push past and build momentum to overcome his inertia that would have increased his speed to go to this peak of 11.57 meters per second. Now, Anning, she would have had great muscles to push her through to get that 10.18 meters per second. But because her momentum was obviously not going to be as high because she's 61 kilograms compared to Bolt's 94 kilograms, she obviously could not maintain that top speed as it went down by almost 3 seconds to 7.66 meters per second nearer the end. Now, obviously, mine, I had to have a turn in mine, which slowed me down a lot. But obviously, that doesn't mean that I could get anywhere near these other two athletes because one, my muscles wouldn't have been as strong as the other ones. I also don't have the best body composition compared to these Bolt and Anning because they will have a higher muscle percentage than they will fat percentage. Now, as we can see, muscle is more dense than fat, which allows for a smaller size of muscle to overcome a bigger size of fat. We can look at velocity. Definition of velocity is that the rate of which an object changes its position in a specific direction. It is a vector quantity, meaning that it has both magnitude and direction. The formula for a vector velocity is velocity equals to displacement over time. Now, displacement refers to the change in position, and time is the duration which the change occurs. Its units are velocity is measured in meters per second. So, obviously, being a vector quantity, it will have a direction on it. So, it'll be meters per second with a direction like north, east, south, west, positive or negative. Now, velocity in sprinting. So, in sprinting, velocity is a primary measure of performance. The faster an athlete can run, the higher their velocity and the better their performance will be. However, achieving and maintaining high velocity requires a combination of biomechanical efficiency, muscle power, and energy utilization. These factors that affect velocity include stride length, so the distance covered with each step. Longer strides allow the athlete to cover more ground with fewer steps. And another factor that affects velocity is stride frequency. So the number of steps taken per second. A higher stride frequency means that more steps in a given time, contributing to a higher velocity. Force production is another factor that affects velocity. This is the ability to generate force against the ground. Greater force production allows for the more powerful strides, contributing to both stride length and frequency. Now, the last factor that will affect velocity is running mechanics. So these efficient running mechanics will minimize energy loss and maximize forward propulsion. This includes proper posture, arm drive, and ground contract. Now let's look at the insights into velocity. So let's break it down into the acceleration phase. So at the start of the race, the sprinter generates maximum force to overcome inertia and reach top velocity. This phase relies heavily on the ATP system, which provides immediate energy for explosive efforts. Now, as we move on to the deceleration phase towards the end of the race, fatigue sets in and the sprinter's velocity begins to decrease. This is influenced by factors such as the lactate accumulation, which causes muscle fatigue, and the energy depletion. So now we're going to move on to the comparison. So in this comparison, we've got Usain Bolt, who Bolt is known for his incredible top velocity, reaching speeds of around 12.4 meters per second, as we've discussed, for his 200-meter sprint. His ability to achieve and maintain such a high velocity is due to his exceptional stride length and stride frequency, which allows for the force, and which is caused by the force production that he is able to complete. Additionally, his efficient running mechanics and energy utilization allow him to sustain the speed even under fatigue. Now, Anning achieves a lower top velocity compared to Bolt, likely around 10 meters per second, while her stride length and frequency are great. They're not at the same level as Bolt's, but her mass is lower, which makes it easier for her to accelerate, but she may struggle to maintain her velocity over the entire race. Now, myself, my top velocity is lower than both Bolt and Anning, likely to be around 8 meters per second. But this is due to less explosive power, less efficient running mechanics, and a lower capacity to maintain speed under fatigue. Practical example of this could be through the calculation of velocity. So we've got our displacement over time, which obviously equals 200 meters, divided by 19.9, 19 seconds, which equals to 10.42 meters per second, obviously with the direction. So Bolt's velocity is equal to 10.42 meters per second. With the directions, we could say north. Now, we could do the same thing with Anning and myself. So Anning's top velocity would be 8.26 meters per second, and myself it would be 5.65 meters per second. As we can see, Bolt's average velocity is significantly higher than both Anning's and mine, which is why he can compete in the race in much shorter time. Now, velocity is a key biomechanical factor in sprinting that influences an athlete's ability to accelerate, maintain speed, and perform at their best. By understanding and addressing the principles of velocity, sprinters can improve their performance and achieve their full potential. Now, displacement is our next topic. So we'll explore the concept of displacement on the slide and its role within sprinting. It's a key biomechanical principle that helps us to understand the efficiency of an athlete's movement during a race. Now, unlike distance, which measures the total path length travelled from point A to point B, displacement focuses on the change of position from start to finish, taking into account direction. Now, let's dive into how displacement applies to sprinting and why it matters. So, the definition of displacement is the shortest distance between the starting and ending points of an object's motion, measured in a straight line. It is a vector quantity meaning that it has both magnitude and direction. It can be calculated through the final position, take away the initial position. So, for example, in a 200-meter race on a straight track, the displacement would be 200 meters in the direction of the finish line. In terms of its units, it's just measured in meters. And displacement within sprinting, so displacement is particularly important. It reflects the efficiency of movement, while distance measures the total path travelled, which may include curves on a track. So displacement focuses on the straight line change of position. This is especially relevant in races like the 200 meters, where athletes run around a curve before entering the straightaway. Now, the key points within displacement are the straight line motion. So on a straight track, the displacement is equal to the distance travelled. For example, in a 100-meter sprint, the displacement is 100 meters in the direction of the finish line. In a curved motion on a curved track, such as a 200-meter race, the displacement is less than the total distance traveled because the athlete is changing direction. For example, in a standard 200-meter race, the displacement is approximately 127 meters, the straight line distance from start to finish, even though the athlete runs 200 meters around the curve. Now let's do a comparison. So we got Usain Bolt, his displacement was 200 meters. He was doing a 200-meter race and he had an approximately 127 meters. So this was the same as Anning, which allowed him to maintain efficient running and mechanics and optimal positioning on the curve, which allowed him to maximize displacement and minimize unnecessary movements. So however, there was a difference on my 200 meters. So I went up 100 meters and then I had to do a turn and come back down for the 100 meters. This meant that my displacement was zero compared to their 127 meters. This was because I finished in the same place that I started. So there was no displacement. But there was a distance change of 200 meters, just like Bolt and Annings. So we have our splits. So on the side, we're going to explore the concept of splits and their importance in sprinting. Splits refer to the time taken to complete specific segments of a race, such as the 50 or 100-meter interval. Analyzing splits provides valuable insights into an athlete's performance, including their acceleration, speed maintenance, and fatigue management. So let's dive in to how splits are used within sprinting and what they tell us about biomechanics. So, the definition of splits are the times recorded for specific segments of a race. For example, in a 200-meter sprint, splits might be recorded for 50 or 100-meter segments. As I've said, the purpose of these splits is to help coaches and athletes analyze performance, identify strengths and weaknesses, and develop strategies for improvement. So, there are four main splits that we use. We use the 50 meters, the 100 meters, the 150 meters, and 250 meters. These can be broken down to just check the acceleration and deceleration phases and see how well the momentum holds up within the athlete. So we can use, we can compare Bolt, Anning, and myself. So Bolt's 0 to 50 meters. So his first 50-meter split is incredibly fast, reflecting his explosive acceleration and ability to overcome inertia quickly. Then through his 50-meter to 100-meter split, Bolt maintains a high speed, showing his ability to sustain force production and efficient running mechanics. Then, as we move on to the 100-meter to 150-meter split, Bolt continues to maintain his speed, demonstrating his superior energy utilization and fatigue resistance. Now, as he moves on to his 150 meters to 250 meters, 200 meters, Bolt's final split shows minimal deceleration, highlighting his ability to manage fatigue and maintain form, also alongside his built-up momentum, which helps him to stop that fatigue, well, to keep going as the fatigue sits in. Now, we're going to move on to Anning now. So Anning's first 50 meters now. Her 50 to 100 meter split, Anning maintains a good speed. Her splits may start to show slight deceleration compared to Bolt. 100 to 150 meter split, so Anning's split continued to show moderate deceleration of fatigue being set in. 150 to 200 meter, Anning's final split shows more significant deceleration, reflecting her lower capacity to manage fatigue compared to Bolt. Now, lastly, myself, so I have in my 0 to 50-meter split, my first 50-meter split is slower than both Bolt and Anning, and I continue like that until the end. Now, the key takeaways from this are that this powerful tool, so splits are a very powerful tool that analyzing sprinting performance by understanding the addressing and the insights provided by splits. Thank you for listening.